Hey, how's it going? My name is Paul, and this is my honors presentation on the physics of vacuum arc propulsion systems. Awesome, so we got a lot to cover. Let's get going. Alright, so one important thing that's relevant to space propulsion is this rocket equation from Tchaikovsky. And basically, the takeaway here is just that because space propulsion systems are all reaction engines, that is, they throw mass out one way to get a momentum the other way. You have to spend fuel transporting your fuel. And that leads to this exponential relationship between your delivered mass and your initial mass. Now, we could get around that restriction if we could refuel space propulsion systems really easily. That brings us to the vacuum arc thruster. Now, the vacuum arc thruster is really interesting because it can use any conducting solid as fuel. And this really sets it apart from other space propulsion systems. It's rarely feasible that you could simply extract carbon or metals from a near-Earth asteroid, and with very little processing, you could convert those into fuel. So the vacuum arc thruster is actually a really simple system. The way that it produces a thrust is it converts part of the cathode material into a high-velocity plasma. And this happens through an arc that happens between the cathode and the anode. I designed and built a very simple vacuum arc thruster, which is pictured here. The cathode was a 6mm copper rod. And here we can see a simple animation showing the design. So the plasma is produced in this arc, but how does the arc get triggered? Well, we actually trigger the arc with a triggerless arc initiation method. And how this works is we put a very thin conductive layer of graphite in my case across the cathode insulator anode boundary, and this drastically lowers the resistance required for a breakdown to occur. If there was no conducting layer, then the voltage required to jump the gap in vacuum would be on the order of 100 kilovolts. So the conducting layer lowers this potential and allows a roughly 1 kilovolt pulse to cross this conducting layer. When this pulse crosses the conducting layer, it produces part of a plasma that the main discharge can flow through. So here we can see a close-up of the cathode insulator and anode, and you can see all the messy graphite coating that I applied with a pencil. And that insulator was actually white, but I put a healthy amount of graphite on there to make sure it would conduct. To produce this high voltage pulse, we need an inductive energy storage pulse circuit. The one I built is pictured right. The circuit actually needs to do two things. Firstly, it needs to provide the high voltage pulse that can trigger the arc, but it also needs to provide the energy to maintain the arc. Here we have the circuit diagram. Let me quickly explain it. So starting on the left, we have the 60 volt lab power supply. Then we have this diode that is simply to make sure that we don't fry this nice power supply that belongs to this. Over here we have the capacitor bank, and the capacitor bank simply provides enough energy to maintain the arc once it's initiated. Right in the center we have a pulse generator. This pulse generator sends a 5 volt square wave. This square wave is then boosted up to 18 volts by this operational amplifier. This is done so that the IGBT, which is this large transistor here, can switch fast enough. We need to have a very sharp switching of the transistor so that we get a high voltage pulse. So let me take you through the charge loop. What happens in the charge loop is the square wave pulse is on. So it goes through the operational amplifier to the gate of the transistor, and then allows current to flow from collector to emitter. So as you can see, there's no resistors here, so we're literally short-circuiting this power supply straight to ground through the inductor. And that sounds like a bad idea. And in some ways it was, because I exploded about 10 different IGBTs in this process. But if we limit the pulse to less than 500 microseconds, it's actually a great idea, because it means we can get a huge amount of current through the inductor, which will build up a very powerful magnetic field. So that's the charge loop. Once the square pulse ends, after 50 to 500 microseconds, the IGBT will rapidly coalesce and there will be no current allowed from collector to emitter. But there was a very powerful magnetic field that was built up in the inductor. So from Faraday's law, this change in the current, which is also a change in the magnetic field, will cause a very sharp voltage spike that will come down and have no choice but to go between the electrodes of the vacuum arc thruster. Here's the anode and here's the cathode. And this causes the pulse that we need to trigger the arc. So here we see an oscilloscope trace showing what I just mentioned about the high voltage pulse. So if we take a look at channel 2, which is this flat line here, this is the current trace. And I used an LEM current transducer to perform this measurement. And I used a measuring resistor that allows us to simply multiply this value by 10. So this value here is actually 59.2 amps, which is a reasonably high current. And then at this point, you can see that the IGBT is closed, and so the current rapidly falls down in the space of about 10 microseconds. What then happens is that this high voltage pulse is seen to rise exactly as the current falls, just like it should. And I used a high voltage probe, and this reading here is a ratio of 1 to 1000. So we have a voltage peak of 960 volts with a current of 59.2 amps. Here we can see the two types of discharge that happen. On the left we have the partial discharge. This is the essence of the triggerless mechanism. And what you can see is a whole bunch of little channels that have not quite yet crossed the gap from cathode to anode, but they have partially crossed. This is called a partial or tracking discharge, and it's followed by what we see on the right, which is the full discharge, which has the full energy from the inductor and capacitor. And as you can see, it's an extremely bright, UV emitting, awesome looking plasma. Now that we've seen the vacuum arc thruster in action, we can very quickly take a look at some of the physics that go on inside of it. First off, we have the cathode spots. This is where the magic happens, and the cathode material is turned into a high velocity plasma. There are extremely high current densities and field strengths, as well as very high temperatures in these microscopic regions, and ultimately it's all of these extreme phenomena that cause the plasma jets to form. Here we have a simulation of a cathode spot, and it shows some interesting features. The one thing that it shows is that the plasma density, which is usually at least 10 times denser than atmospheric pressure, coupled with the ion bombardment, actually heats up and drives down and almost burrows or digs into the cathode material. And that's how you have all this molten cathode that actually gets turned into both high velocity gas and plasma. And one more thing we can note is this little molten microjet, because we actually observe some of these microjets which become microdroplets at different angles, and we'll see that later. Earlier this year, a paper used a focused ion beam to actually take a cross-section of the cathode spots. And this is pictured here. And this can give us some insight into these craters that are formed by these really high density plasma jets. The cathode spots also have some very interesting fractal properties. And these have been compared to simulated results of Lichtenberg figures. And you can actually produce a probability relation that relates the potential of the field, the electric field in the cathode spot region, to the probability of an ignition. And what you see, this eta parameter here, this is the proportionality constant. And it's actually been found that eta is 1, which means that the field strength and the ignition probability are directly proportional, which makes perfect sense. The cathode spot motion, which is usually random and fractal in nature, takes on a non-random component once the vacuum arc thruster is put into a magnetic field. This is known as retrograde motion because the cathode spots move in the anti-Amperian or retrograde direction. This is the exact opposite direction that you would expect from the Lorentz force. There has been recent research on the magnetohydrodynamic effects that cause this motion, and I gave a full derivation in my paper. But pictured on the right, you can see a summary, which is a vector diagram that I produced. And what we can see here is basically a cathode spot, and this J vector would be from anode to cathode. So the anode would be left of center, somewhere back here. And the point to realize is that there is a self-magnetic field that usually is completely balanced. And this self-magnetic field is simply the magnetic field caused by the current vector that goes from the anode to cathode. But now, because we have an applied magnetic field, which you can see is pointing out of the page upwards here, that means that now, whereas before the self-magnetic field was symmetric, now it interacts with this external field, and what you get is a larger pressure on one side than the other. And this results in this magnetic pressure vector. There are other effects that come into it, like the magnetohydrodynamic effects, and specifically the kinetic pressure of the plasma. And you'll have to check out my full report for a discussion of that. But the point is that this pressure vector points in the anti-Amperian direction, and this could really be the reason why we see this motion. Now that we know more about the physics that take place in a vacuum arc, we'll quickly return to some experimental findings of the phenomena that were observed. Firstly, we can see some cratering and ablation of copper. On the left, we can see that after several pulses, there are entire regions where copper has been ablated away from the cathode. And we can also see two micro droplets towards the bottom here. And these micro droplets are little pieces of molten metal that were dug out of the cathode spots and landed there. On the right side, we can see more cratered regions. This has got to be my favorite slide, because not only do we see three amazingly bright plasma pulses, but we can also see that those little micro droplets that I mentioned being dug out by the high velocity plasma jet have actually left the cathode spot, and we can see their streaks on these images right here. Here we see a slow motion sequence of the plasma and macroparticle plumes. So first image, we have the plasma pulse. Remember, it's moving at around about 20 kilometers per second, so we only see it in the first image. About 8 milliseconds later, we can see the macroparticle plume, which is very hot, continue to expand and cool as we go down the sequence. Finally, we look ahead to a possible improvement on the vacuum arc thruster, and that would be to add a secondary acceleration stage and turn it into a vacuum arc ion thruster. The preliminary research that has been done on this shows very promising results. Thanks for listening to my project. Hope you enjoyed watching the plasma photos as much as I enjoyed making them. And cheers.